Hi, we're going to start with taking a look at radioactivity, in particular alpha decay, so we could understand what uranium would normally do under regular everyday circumstances, like the uranium rock that is sitting underneath many of our houses. Okay, I'm going to start with polonium. I've got this periodic table right here that is just showing atomic numbers. So here's polonium, atomic number 84, and lead, atomic number 82. So that's going to become important in just a second. So I'm going to come back here, and what I'd like to do is show you what's going on in alpha decay of polonium using this animation. Take a look over here at the legend, these particles. Okay, it shows you what color a neutron is, what color a proton is, and then we've spoken briefly about alpha particles, and so you can see that. So I'm going to hit play, and all of these atoms are radioactive. They're unstable. They're not going to stay polonium forever. And as you take a look at those individual nuclei, unstable nuclei, what you'll start to notice is that some of them are going to start to have this kind of yellow glow around them. We'll talk about what that is and why it's represented that way. And see if you can notice what is released as it does that kind of yellow glow. What is leaving the nucleus? Okay. All right. Use the legend over here to figure out what that was leaving the nucleus, if you haven't figured it out already. And so we've started out with all polonium. Again, polonium has that atomic number of 84. All right. Looking at what's going on here, it lost an alpha particle, which has 2 protons. So if it lost 2 protons, it's going to go from 84 protons to 82 protons, which makes it lead. It lost a total of 4 particles from the nucleus, which is why it goes from 211 to 207. All right. So we're going to leave polonium and we're going to head over to uranium. So taking a look at uranium over here, right here, 92 protons. And in particular, we're going to take a look at, where did it go? Interesting. Now we're going to take a look at alpha decay of uranium. Again, we've got a key here. I'm going to have right equation here. You can see that we're starting with uranium-238. And we're going to watch what happens inside this nucleus as it undergoes radioactive decay. I also want you to pay attention right underneath where it says gamma. And it didn't do it, but you saw like little rings show up, okay? And so again, alpha decay, if we reset and I play it again, you can see what's wiggling. And so what's wiggling is 2 protons, 2 neutrons. They're going to leave the nucleus. And so if 2 protons leave the nucleus, we're going to wind up with 90 as our atomic number, and which is thorium. 238 minus 4 is 234. Okay. And then our alpha particle, right? 2 protons and a total mass of 4. I wish it didn't say helium because it's not helium. Okay. So typically what uranium will do is undergo alpha decay. Okay. When this happens, an amount of energy gets released. And so what I'd like you to do now is turn to page, let's see if I can do this, 1 of your packet. Turn page 1 of your packet and come down to number 3. Okay. So under radioactive decay or any nuclear reaction, energy is released, more energy than you would expect to be released. And so I would like you to pause and take these notes under that number 3 on page 1. All right. So I'm reading again from the book Shockwave. It's just a small segment, and this is the part where they are, I can't get this to go away. Exit slideshow. Okay. Where they are gathering the plutonium material. And what's it going to do here? Okay. All right. So with regard to what's going on, and let me come back to here. Where's my the right one? So this is what's going on inside the plutonium fuel. Okay. 9 men, including Morrison, stood around the table on which the plutonium hemispheres now rested on sheets of brown paper. All the men were wearing white surgical coats. One of Morrison's colleagues, Robert Backer, turned to an Army general and asked him to sign a receipt for the plutonium, worth at least several millions of dollars. The general, Thomas Farrell, jokingly asked if he could hold it first. He wanted to feel what he was buying. He put on a pair of rubber gloves and picked up one of the hemispheres. I'm going to pause. These hemispheres are metal. So think about what metal feels like when you're holding it. Okay. Back to the text. It was smooth and heavy, and it felt curiously warm to the touch, as if it were alive. What Farrell was feeling was the energy released from radioactivity. The artificially created element was literally breaking down in his hands, the unstable nuclei of his atoms, ridding themselves of billions of alpha particles in a bid to regain stability. And as they did this, they returned mass into energy, which was the warmth that he felt. So on the screen, all of that kind of yellowish orange that you're seeing is trying to depict the fact that energy is being released. So that's it for what typically is going to happen with regard to radioactive decay and uranium.